We are the leading team, and so that's why our name is the first one. And so that was a good experience. Now, the one for I'm not going to wait too long here. I'm going to hand this to the teammates themselves, and Arusha is going to take over.
Hi, my name is Arusha Bhargava, and I live in Hillsborough, New Jersey. I'm going to 8th grade at Hillsborough Middle School this fall. I'll be giving the overview of the game. So the goal of the game is to collect exactly 24 samples from 3 random sites of 9 sites that we know. We only get to know these sites right as the game starts, so that's a hard challenge for it. And then we have to deliver the 24 dust samples that we collect back to the base within 180 seconds. To win the game, we had to write program on an MIT website to control NASA's Astronaut satellite that's currently in the ISS. And we had to complete this mission with the least amount of battery use in the shortest amount of time. Our program was executed on the ISS by astronaut Dr. Woody. You can see in the picture that's not upside down. He's just on the ceiling. He's on the ISS with the bumblebee that we used. That was the astronaut that we used. Our team name is Coach Engineer. This is our team of around 20 people. We had 2 high school mentors, Aditi Gopalakrishnan and Ishan Verma, who just graduated this year. This is our timeline. We started with our first submission on July 14th, where we all had our own different teams and we wrote our own code. And at the end, we had our internal competition. And then 2 weeks later, we had the final ISS submission where we all came together and we tested our 3 main sets of code that all of us created together for further improvement. This is a link to our team portfolio that we came together to make in the last week. That's the QR code to see it, and the link is also down below. This is going to be, the rest of the presentations is going to be an overview of our 3 main algorithms and our core strategy. Our core strategy was to go through the certain algorithm that we use, and we were going to use it to optimize the path that the satellite has to take and its corresponding actions by minimizing battery use, distance, and time. And now to discussion on our 3 programs. So the first program was made by Maya. Julia unfortunately could not be here today, and the second one is made by Dennis, the third one by Vedaang. You'll get a chance to hear about all 3 of them today. The first one by the 3 of us was called Permutation through Iteration.
Hi, I'm Maya. I'm going to freshman year at High Technology High School. Unfortunately, Julia couldn't make it, as Arusha said, but she will be a freshman this incoming fall at Bridgewater High School.
This is a basic overview of our code. We made a program that loops and iterizes through all of the different permutations that the satellite could possibly take, and then we check them to see if they would equal to 24. The cases that equal to 24, we stored all of their information into an array of around 20 by 6 to count for all possible cases. Each column represents a different path that the robot could take. For example, the first path, if the active sites were 3, 5, and 6, the first path would be 3 plus 5 times 3, and the second one would be 3 times 6 plus 6, so on and so forth. Each row represents something different. The first row represents the case number. This is important for the code to key back into the certain path and its information later in the program. The second row is the first site number. This is the first place that this certain path has to go to. The second one is whether or not the robot is multiplying or adding at the next site that it's going to go through. Then it's the next site, site number 2, that the satellite has to go through to complete this path. This goes on for around 4 more rows just to count for larger cases. This is our flow chart. We start with module A, and module A, it just checks to see if there are any more possible cases and permutations and combinations that the satellite can run through. If there's not, we exit the loop and we go to D. Otherwise, we continue to B, where we check to see if this certain combination combines into 24. If it doesn't, we just exit out back to A, but if it does, we calculate the score using battery time and distance and store it in the previously mentioned array. Then we go back to A to complete the loop. Once A gets terminated, meaning A becomes false and there are no more possible routes, we go to D, which compares the scores written in all of the arrays, and it selects the highest scoring one, where module E will execute this path. Now to Maya for more details.
Okay, so first let's illustrate how we find all the permutative paths in modules A, B, and C. Okay, so this is it's a demonstration of how we use 3 nested for loops in order to iterate through all the possible site combinations. So this green I for loop, there's no calculations done in it because obviously you can't calculate anything with only one site, like that won't get you 24. In the J for loop, however, there's one instance, which is site A times site B here. So for example, that'd be like 6 times 4, 8 times 3. Well, that's it. But say you have sites 6 and 4 in your active sites. So the first thing it would consider, it would try and save, it would end up saving 6 times 4 and 4 times 6 into the array to calculate it later. And in the K for loop, it considers 3 different sites, and there's a lot more different combinations there. Okay, next, I'll illustrate how we calculate and execute the best possible path found in modules D and E. Okay, so in this blue section here, we calculate and we loop through the entire final score array in order to find the path which is most efficient. In this E section, the red, we iterate through the column containing the best path and we execute it. And then we go to base and deposit the samples, and then we can get our score. Okay, so that concludes our explanation of our algorithm. So if you have any questions, feel free to ask.
So why the 24? Is it because the best pass and collect all the samples?
24 is the requirement to for the competition. So you get like a score of 10 if you collect 24. If you don't, you get a penalty. So yeah, so you need to get exactly 24.
What determines whether you do the addition or multiplication?
That's the only 2 possibilities. You can't like divide or subtract.
Okay.
So yeah, you can multiply or
Right, but what decided what this is 2 number, for example, 3 and 5, you can do plus, you can do addition, you can do multiplication.
Mm-hmm.
What determines you're gonna do addition or multiplication?
Okay, so going back to where we have the different calculations, like here, I'll go back. So yeah, so right here, we have that. These are all the different routes we have pre-planned, but we can just change the site numbers, and it literally just checks all of them, brute force, if it adds to 24 in the end. Does that answer? Yeah.
That makes sense.
Okay.
Thank you.
Yeah. Okay. That's it. Oh, any more questions?
Any other questions?
Yeah. Okay. Thank you. Oh,
Now
hold on.
to Dennis for his permutation through recursion.
Yeah. Okay.
Hello, my name is Reznik. I'm going into my freshman year at Churchill Junior High School in East Brunswick, New Jersey. So for a basic overview of the program, it will use the recursive function to permutate over every possible path. And if a path that reaches 24 is found, it will calculate the score of the path using the battery score, the time score, and the collection score. And depending on which score has the highest path and depending on which path has the highest score in the end, it will navigate along that path. So for the function, the program uses recursion to look more elegant and shorten the amount of code. And the program takes advantage of the recursive call stack to construct a tree of actions. For every action, the function is called again, which is the recursive part of it. And every call, the amount of actions remaining goes down by 1. And once there are no possible actions left, the program will return. So for the tree of actions, there are 3 parent nodes, depending on which action you want to choose first. This is a more simplified version of it, with only 3 possible actions as opposed to 6 in the real game, because I could not fit that on 1 page. So at the start, there are 3 possible actions. And once you go down a level, you cannot repeat that action again as per the game rules. So now you only have 2 actions and 2 child nodes. And once you pick one of the child nodes, you cannot repeat that again. So you end up with only 1 child node, and that's your final action. And you could see over here that depending on which path you go down, it constructs like a series of numbers. And this is all the possible combinations of 3 numbers, so 6 possible paths. For score optimization, the score calculation uses the battery score, time score, and collection score as previously mentioned. The battery score depends on the distance and the held samples. So as those 2 values increase, the battery usage will increase, resulting in a smaller score. The time score is how much time is left after ending the game. The whole game lasts only 180 seconds before it automatically ends. So depending on how much time you have left after ending the game, you will have a higher score or a lower score. And the collection score is the number of deposited samples. So you want to deposit 24, but for every sample away from 24 that you deposit, you receive a penalty to your final score. So you want to try to get 24 every time. So this is a basic flowchart of my program. You can see that the dust over here starts at 24. This is because my program, it will work backwards. So for the criteria over here, which is the main condition of the program, checks if the current dust is 0. If this is true, that means a combination has been found. Otherwise, it will go through all of these modules, and each module represents a different action. For example, like duplicate dust at this site, add dust at the other site, and so on. So we'll go through all of these modules until it goes back up to here, and it will check if it reaches 0 dust. If it does, you found a combination. Otherwise, it'll keep going. Okay. On the next slide, I'm going to zoom into this criteria condition to give like a more in-depth explanation. So the first thing that happens in the criteria is it will check if all the permutations have been gone through. If this is true, it will find the best path out of all of the possibilities you went through and navigate along this and end the program. Otherwise, it'll check if the current path is valid, meaning it reaches 24. If this is true, you found the combination and you'll loop back up to here. Otherwise, you're going to go through all of these modules again. Next, I'm going to zoom into these 2 modules. So this module 1 right here represents duplicating at site A, which means the first active site. Module 6 over here represents adding at the last active site. So to zoom in, it starts off by checking if you already did the action, because again, you're not allowed to repeat any actions. If you haven't done it, it will check if the current dust divided by the dust at site A has a remainder. If it does have a remainder, if it doesn't have a remainder, that means the action is valid and the program will try that. But if it has a remainder, that means you cannot do this action and it will just move on to the next module. For module 6 over here, which is addition and not duplication, it will also check if you already did the action, but this time it will check if the dust minus the dust at the site is negative. If it isn't negative, then it will try the operation. Otherwise, it'll skip it. Okay. Yeah, that is all. Okay, any questions?
Why did you decide to start with 24 at the beginning and then down more efficient?
Yeah, it was more efficient from what I found. Anything else? Yeah. So once the program, it finds that a path won't work, it'll just instantly like return back. That's why it's faster to start at 24. Anything else?
How did you learn about recursion?
From her. Okay. Anything else? No? Okay. Next is Vedaang's algorithm. It's called permutation using Heap's algorithm.
Hi, my name is Vedaang Verma, and I'm an incoming freshman at Bridgewater Riverton High School, and this is my algorithm. So the main process behind my algorithm is to first generate all possible permutations of the path. Then we find the path that yields the best score and simply execute this path. Now this sounds simple, but there's a few key procedures that make this possible. The first one is a function called getPermutations. This generates all possible orderings of 7 actions in the game. These 7 actions are collecting at each site, duplicating at each site, and then ending the game. This is a recursive function, which basically means it calls itself over and over until it gets the job done. Then there's also a function called getScore, which simply calculates the score of a path if it was to be run. Then there's the execution, which stores the best path in an array and simply runs it. So as I mentioned before, to get all permutations, we use a recursive function. But before I get into that, I just want to show a example unrelated to the game, which basically will get you guys the basic idea of permuting. So here we have 3 numbers, 1, 2, and 3. The first step is to choose a term to be in the last spot. Well, we have 3 choices for that, either 1, 2, or 3. Then we forget about the third spot and look at the second spot. And we find that for each of these choices, we have 2 choices for the second spot. And then for the first spot, you only have 1 choice remaining. And that leaves us with 6 total choices for the permutations of the numbers 1, 2, and 3. With this, we can derive a basic procedure. And that procedure is to first choose a term to be last, then isolate that term from the rest. And then we repeat this with the remaining non-isolated terms. So you're kind of working backwards through the list and ordering them. At the end, each term has been in each spot, generating all permutations. Now that we've got the basic idea of permutation, let's look at how we apply it to the game. So instead of permuting numbers like 1, 2, or 3, we have 7 actions, and they're just collecting at each site, duplicating at each site, and then ending the game. So this is a recursive function, as I mentioned before. So it calls itself 7 times in total, and it creates what's called a stack, which is like a bunch of work the computer has to do. It has to work through all of these 7 layers of the stack. So the first call, which is the 7th layer, the bottom layer, it has all 7 actions. But you're going to notice the second call, the 6th layer, only has 6 actions. The reason for this is it's almost like isolating the last term, like I showed in the last slide. We're simply isolating the last term each level. So each level has 1 less term than the last. So how it turns out is that if at each level we choose the last term, or in other words, these terms, we're choosing a term for each spot. So that's the basic idea behind our permutation. Just choose the last term at each of these levels. If you want to think about it this way, you can just think that each level is responsible for choosing the action in that slot. Now that I've shown you the stack and its application to the game, let's see how the code actually moves through the stack during runtime. So in order to keep things brief, I'm not showing all the movements, just the major ones. So here's the same stack, except with arrows this time. And one thing you want to, again, keep in mind is that each level determines the action in that slot. So this determines the first action, this determines the last action. And so the first thing it does is it starts at level 7 and then goes all the way up to level 1. Every time it reaches level 1, a path is completed and the score. So what this basically means is at level 1, you only have 1 term. You can't order 1 term anymore, so you've just completed a path. So it reaches level 1 and it calculates the score, but then it goes back to level 2 and it works through all the possibilities of the second action, each time going back to level 1 to calculate the score. Then it works through all the possibilities of the third action, all the possibilities of the fourth action, and so on and so forth. And eventually it's worked through all possible permutations, and that's how we generate all permutations. So now that we've seen the get permutations function, let's look at a complete model. It's back. All right. Let's look at a complete model showing how it interacts with the rest of the code. So to start off, we have a variable, an integer called size set equal to 7. And size is just the number of actions you're dealing with right now. We start at level 7, so we're gonna set size to 7. Then we ask if size is 1. So size is 1 is basically saying, have we reached level 1? Remember in the previous diagram, level 1 just means you've completed a path and you can calculate the score. So that's what we do. We get the score and then we ask ourselves, is the path score the greatest so far? If it is, we save it as what's called the best path. If not, or either way really, we return to the previous stack and keep going through this to get permutations. Then this next part is essentially finding the new last term for whatever level it's on. And remember, finding the new last term is basically the heart of this algorithm. So the reason we're repeating size times here is because let's say your size is 5, you have 5 terms. So you have exactly 5 choices for the last spot. So this ensures that you get all, well, say 5 choices for the last spot. So here we do get permutations, and this entire function is get permutations. So it's essentially calling itself. This is the recursive part, and it creates a stack. You're gonna notice that size is set to equal to size minus 1. So we're decreasing size by 1, which is essentially isolating the last term as we create a new level for the stack. Then we find a new action for the last spot of whatever level we're on right now. So we keep doing this, and this is gonna eventually generate all permutations. That takes a while, but eventually it exits to navigation and goes to the navigation module. So at this point, I'm gonna open the floor to any questions. Anybody?
Hi, we have a question regarding the get score.
Yeah.
How do you, so the project specification didn't say anything about the time that it takes to travel from one site to another. So how did you use that input?
Yes,
time?
that's a good question. So we have a get score function as I show right here. Essentially what it does is it just calculates the score. Now I chose to focus more on the permutations part because that is a bit more of the meat of my algorithm, I'd say. But get score essentially what it does is the Zero Robotics provides functions for us to get the battery and get the time consumption. So we can simply use those functions to get the score, and it's fairly trivial.
But then did you measure the time, what it takes to travel between 2 sites? Because I don't think that was, okay, so you just did some experimentation and then used those.
Actually, as a team, we did a whole lot of data collection. I'm about to get into that, where we basically took the time of our runs and saw how much time it took to move. And that was basically the testing that we did, and it helped us tune some parameters and variables in our algorithms.
Yeah,
And
that makes sense. Thank you.
all right, any other questions?
Can I ask you a question about the first algorithm that I didn't quite think of earlier?
Sure. I think the other people would be better suited to take that.
All right, oh, then I'll wait.
What's your question?
So how did you use nested for loops? Because when I tried doing it, it would give me an error that it wasn't allowed to do that.
Are you using block code or?
Yeah, we were using the block code.
We wrote it out.
Yeah, we wrote it in.
Oh,
Yeah, so that might have been like an error in
yeah.
something like that. Okay. Any other questions for anyone? No? Okay, cool.
Just to answer your question very quickly, I understand it's painful using broccoli. I have to admit, I mean, it kills me. I mean, I try to create some environment for the younger kids, attempting to get them learn the C and C++. My God, I think I lose 10 years of my age just to play it. It's just very difficult. So unfortunately, but then it's very intuitive. Now, what I would recommend you to do then is when you do the broccoli, when you do one block, one loop, just translate and see, take a look and learn from it. See the structure, how they relate to one loop. And then you do another layer, translate back to C, and then try to make that work first. Once it works, then you go back and you probably can extrapolate what the third one should look like, right? So if you want to learn it from broccoli to C or C++ that way, you need to do divide and conquer, one step at a time. Do not do all three. I mean, I would die if I were I would do that. So I would do one, translate to C, take a look, read it and understand it, play with it, and muck with the variable or whatnot. Once you understand it, do the second block, the next loop, do that again, translate back to C and look at it again. Once you understand the double loop, the third loop is just like pre-intuitive. So that's my recommendation. Okay, but I would never want to look at broccoli again.
Doctor, you want to come back? Maybe you're London. Okay.
Another chance to ask questions before.
All right. So before I move on with the presentation, are there any last minute questions for my algorithm? Let me look at the chat real quick. Does not seem like any more questions. So I will keep going with the presentation. All right, so now we have to think about how do we determine which one to submit. We have many algorithms and we have to figure out which one is the best for submission. So for the final submission on July 21st, we had to figure out which one of the three algorithms would be best to submit through data collection, and this was very important. So for data collection, we created a performance matrix, and this basically stored a bunch of our simulations, keeping in track the total score, time score, battery score, all of that stuff, so we could evaluate all of our paths and scores. So with the data collection, we were able to see any issues with the algorithms and find any inconsistencies. We also were able to observe how various paths affected the battery usage and the time usage. So one big hurdle for us was that the simulation environment didn't allow us to control the active sites. And to get around this, it was a big team effort. We just had to run over 400 simulations, which took a lot of time. So we found a few issues with the algorithms through data collection, which is basically the entire reason we do it. One thing is the velocity that we found during our simulations was different from what was stated in the game document. We contacted some of the Zero Robotics officials and we verified later that it was just a typo. But this actually helped us because we could correct this in our algorithms and get higher scores. We also found multiple optimization errors within our algorithms that we could swiftly correct. So with our performance matrix, we had to observe and evaluate. We would evaluate the battery and time consumption using various paths to make sure that we're using the optimal routes with each algorithm. And then we look for two main parameters with the data collection. The first one was, have the algorithm selected the most optimal permutation? Or is there any ordering of collection and duplication that yields a higher score? Then we also had to ask ourselves, is it worth it to drop off partial samples? Which basically means during the game, midway through the game, do you drop it off at base and then keep collecting? Or do you just get everything and then collect at the end? We found that it was more efficient to get everything and collect at the end, but it was good that we tested it out either way. So with our data collection, we came to a final conclusion based on the three algorithms we have presented to you today. So we found that the three algorithms were actually quite close, but algorithm 3 was the slightly higher in consistency and lower in expressions in code. If there's a tie and score during the competition, they will actually take this into account. So it's important that we looked into that. So we'll make a full video of this presentation available at YouTube and we'll also post it to the Piazza forum. And before we end with a Q&A, I just want to show you guys a quick video of our robot running on the International Space Station. So let's go over here. All the way to the beginning. There we go.
Eric, I copy. All right, alliance number 6 is QU Coffee. This alliance represents teams from Clark Charm Jr. in New Jersey, another team from Little Slinger Community School in Navajo Nation, the Mid-Valley Family YMCA in Los Angeles, California, Team Eureka from Puerto Rico, and the O'Malley Middle School from Gloucester in the great state of Massachusetts. This is the first year for Clark Charm Jr. and Little Slinger Community School. Good luck to you, Fox.
So it actually takes a while to start up. So just sit tight for a minute.
Astronaut actually follows the city.
So that's something just suspending there.
Alright.
Yeah.
They should be starting very soon. As long as that.
You all have to kind of visualize the line green there. So 1, 2, 3, 4, 5, 6, 7, 8, 9.
It's like an invisible grid. You could imagine that as a center at 5 right now.
Oh, we can see another astronaut in the background. A quick wave. Look at that. Oh, 2.
So he's using sign language to tell us what
Actually,
size. The first one is 2.
3. Oh, wait,
No, 6.
6, because we can see it like that.
Instinct got me.
I
6,
know.
2 and 6.
And then here, Astro B has to do a bit of a reset, which is pretty interesting.
Astro B appears to refuse the 6. Maybe he's rebelling against Woody. He's like, I don't want to do a 6. No worries, we'll presume.
So I'm
shortly.
gonna just
we're
skip
gonna-
to when our run actually happens. It's gonna take a while, as you can see, but I think it's right around here. Get the flashlight.
So we can see it here. Right off the bat, if we use all 3 numbers, I think we can do maybe 2 times 9 and then add 6. But I think there might be another path as well.
Shorter path.
Yeah,
All right.
So it's at 2.
it's
Uh-huh.
the
We
sites are
can
269, by the way.
Multiply by 2 and then multiply by 6.
Oh, because that would be 2 times 2, which is 4, and then
Times 6.
times 6, which is 24. And so we could see it collect 2. So I guess we'll figure out here what path we decided to choose. Oh yeah, they are duplicating, so they will be going the
Nice.
second
Alright.
path. So this alliance is, they did a great job. They used recursion. They actually used Heap's algorithm, and it is basically recursion.
Recursion is like when a function calls itself. So you might return a value from a function, aka the function like tells you some information at the end, but then you can reuse that information and call the function within itself. It's really strange, very like functionception.
Yeah,
So it's very good for things where you have to like repeat certain code a bunch of times and like keep track of where you're going. So one example is like here, it might be helpful for searching
Yeah.
a bunch of like possibilities. So maybe you start by trying site 2, and then after you've tried site 2, you recall the function from within itself and try the next site and try the next site. So recursion is very good for sort of complex ideas and trying all the possibilities in like a
Oh,
possibility.
there's the light.
tree.
Successful run. Round of applause
Nice.
for Alliance 6. Yeah, recursion is another way.
Alright, so I'm gonna
of
skip a bit further
a program, and
to
it's very
the end
similar
when they call our name.
to use.
Oh, should we put this run as well or skip to the end?
The final run?
Yeah.
Yeah,
Okay.
final run. is
Okay.
Because you guys decide to optimize one side up, right?
Yeah. All right. Here's the final run.
Two. 6, 7, 8. All right, let's see. It looks like they're going to site 2.
I think it was 1, 2.
Awesome.
Yeah, it was 1, 2.
I'm thinking maybe they'll go to 1 so that they'll have 3 in total and then multiply by 8.
Okay, yeah, I like that plan. This code also did a great job. They had code that actually computated all of the different paths and the scores of each path. So say that there was 2 different paths you could take, they would compute the score for each and then choose the best path. So that was very cool to see.
Oh, looks like they're going down to 8. Maybe they're gonna go for 2 times 8 plus 8.
Oh. That'd be probably the best move because they're only going to 2 sides instead of 3. So as you can see there, it is going to 8. And their code did successfully choose the correct path. So as you can see here, they had 2 different options and it did take the path that would take the least amount of time. So great job to that team. It was, all right, we can see it. And now it will go the other way and add those 8 samples. And here we can see it.
Imagine doing pull-ups up there. I would be so strong.
I know. You could have the world records. And so here we can see it going to start moving back to home base. And there's the light. Congratulations.
All right.
Amazing job. Amazing.
So let's skip to the end.
So with the other 2 alternate, you just stick to them first, then we'll find for it? Yeah.
Yeah.
The beautiful thing he did is that it doesn't matter if 3 sides, 6 sides, no side, the way he wrote it, and take any. But you figure out that 2 sides, you have these. Okay, just got the 2 numbers, right? Right, the one thing is that they do not huckle any.
Future endeavor.
So you
Take care from the space station.
Oh. Probably.
Congratulations.
Yeah. Yeah. Probably where he's talking.
Amazing job. Amazing job.
Master BMIT on Science 5. We are live with the students and we're ready for some very special news from our crew. Over to you.
Excellent. Atila. Woody, to be back with you live on Space to Ground 3 for the final conclusion of our Zero Robotics event this year. All right, thank you, Eric. Well, congratulations to all the participants. I know you guys worked hard, and it was really cool seeing your code running up here on board the International Space Station. So great work to everyone. It's a real honor to get to announce the podium for this year's 2023 Zero Robotics. So without further ado, in third place this year, we have Alliance number 5, the Masters of the Universe. Let's give them a round of applause. All right, next up, in second place this year, we have Alliance number 4, the Robo Rebels. Round of applause for them as well. All right, and finally, the winners of the 2023 Zero Robotics Challenge. We have Alliance number 6, QU Fozzie. Congratulations.
All right, so I'm gonna head back to our presentation here. And we're just gonna have, first of all, I wanna thank you all for listening, and we're just gonna have a Q&A to finish things off. So any questions you guys have for any of us?
Well, we thought you had to submit the code in block code, but like how exactly, like what did you submit in C code or in Blockly, or like what did you submit it in?
In the Zero Robotics website in the IDE, there was an option you could do block coding or you could do C coding. We just did our entire thing in C coding, and we just submitted that.
I thought you weren't able to use the C code editor.
We were able to. It should be like an option when you open up the menu. You can choose like block coding, coding in C++. So we
Yes, so like so you can switch like back and forth, or is that what you mean? Or
I think it's when you create the project, you can choose block coding or C coding.
okay, because I thought that it had to be this block code.
Yeah, you could also do the block coding first and then translate it to C and then try working from there, you know, like translating back and forth. You could try that.
Okay.
But you can't do it C to block coding. Just make sure you're doing block coding to C.
Okay.
So any other questions for any of us?
No.
Yeah.
What's the second place?
They didn't they did not tell us. Yeah, they didn't tell us the scores, but they just told us the places. Yeah.
Good job.
Thank you. Yeah, all right. Thank you. All right.